Example: a compact disk rotates from rest up to an angular velocity of minus 31.4 radian per second in a time of 0.892 seconds. What is the angular acceleration of the disk assuming the angular acceleration to uniform? Through what angle does the disk turn while coming up to speed? If the radius of the disk is 4.4 centimeter, find the tangential velocity of a microbe riding on the rim of the disk when t is 0.892 seconds. What is the magnitude of the tangential acceleration of the microbe at that given time? Again, this is just a simple application example to apply the new equations that we learned. So here, alpha is omega, the change in omega by the change in time, or just divide omega by t because the original omega is 0, so the final omega minus 0 is just omega itself. The same for time. The initial time is 0, the final time is this value. So we have alpha, the angular acceleration, and minus is just to tell us that this is clockwise. When you see minus, you understand the direction of rotation is clockwise. Okay, so both omega and alpha are clockwise. Then for the angular displacement, we apply the kinematics, omega I t plus half alpha t squared. Omega I is 0. The initial angular velocity is 0. It started from rest. So we have just 1/2 alpha t squared. This is alpha. T squared 0.892 squared. Evaluate. This is about 14 radians. And again, it is minus, which means it is clockwise. Then for the tangential velocity is r omega. R in centimeter, we need to change it to meter because we have to be using SI unit all the way. 4.4 centimeter is 0.0445 meter, right? We multiply that by omega, so we get the tangential velocity as minus 1.4 meter per second. Then for tangential acceleration, it is r alpha. This is r and that is alpha. So it is minus 1.57 meter per second squared. I hope that now we have a better understanding for the variables of motion and how to relate the linear variables to the angular variables, and also how to calculate the tangential velocity and tangential acceleration from the corresponding angular velocity and angular acceleration. We move on to the centripetal acceleration. So we have tangential variables and we have centripetal acceleration. By centripetal, we mean the acceleration toward the center. Stay tuned in order to understand all about centripetal acceleration. If we consider an object moving in a circular path, like this car here, the motion will have constant speed. So a change in position with time, which is the speed, is constant. The magnitude of the velocity, which is speed, is constant. But the direction of the velocity is changing all the time. Each moment, the velocity changes its direction. Okay? So, although the magnitude is constant, the magnitude of the speed is constant, but because it is changing in direction, then there will be a change in the velocity, because a change in any vector can be a change in magnitude or a change in direction, or both. In this case, the magnitude is constant, but the direction is changing. Therefore, there will be an acceleration for this motion. This is an accelerated motion. This is an accelerated motion because the velocity direction is always changing. Okay, at some point, this is the velocity vector, v initial. At some other point, b, this is the velocity vector, v final. It's true that the magnitude of this vector is the same as the magnitude of this vector, but the directions are different. Because of the change in the direction, there is acceleration for this motion. This is the thing that we will learn about now, which is called the centripetal acceleration. Usually, we use this symbol A sub C, C for centripetal. The one that we learned earlier, A sub T for tangential, okay? So now we are talking about a different acceleration. This acceleration is directed toward the center. Okay. I will prove in a minute that the centripetal acceleration is equal to v squared over r. So here, let's examine this vector diagram. This is v initial, this is v final. We are interested in the difference, v final minus v initial, right? This is a vector equation. This is a vector equation. So we will apply what we learned in vector algebra. You have v final, this is v final. And now I am interested not in v initial, but in minus v initial, because I need v final minus v initial, right? So this is v final. And for v initial, this is minus v initial. So you have this vector, and this is minus v initial. When you add v final to minus v initial, this is the result. This is the resultant vector, delta v. And you can see that the resultant vector is going toward the center. The direction of delta v is going toward the center. Aha. So now we understand from where the centripetal acceleration is coming. It is coming from the continuous changes in the direction of the velocity. And delta v will always point toward the center. Okay? Now about the magnitude. If you take this triangle and this triangle, we are dealing with the same angle theta. These are two similar triangles. So the ratio between delta v and v, because this side and this side, they are equal in magnitude. V final is equal in magnitude to v initial. Okay? The ratio between delta v and v is the same as the ratio between delta s and r and this other triangle. So from this relationship, we find that delta v, in fact, is v over r multiplied by delta s. Okay? Now, if we divide by delta t, delta v by delta t is the acceleration a, and delta s divided by delta t is v. Delta s divided by delta t is v. V multiplied by v is v squared. So the new acceleration, the average value for the new acceleration, which is directed toward the center, is v squared divided by r. V squared divided by r. This is the centripetal acceleration, the acceleration toward the center. Okay? Any question here, or you understood the concept? Any question? If you have any question, just unmute your mic and ask, please. Okay, I assume you are doing well. So the centripetal acceleration is v squared over r. This is different from the tangential acceleration that we talked about earlier. If we substitute for V equals R omega, therefore the centripetal acceleration is equal to V squared, which is R squared omega squared divided by R. We can simplify. You have R squared divided by R, so this is just R. So the centripetal acceleration is R omega squared. The centripetal acceleration is R omega squared. Now we check the dimensional analysis. We know that R has a dimension of length, omega has dimension of per second, so it's 1 over t. And the acceleration, as always, dimension of length divided by t squared. This is what we have here. R omega squared, R is L, and omega squared is 1 over t squared. So yes, the equation is correct. So we are done with the variables of motion. You have two accelerations. The tangential acceleration is R alpha. The centripetal acceleration is V squared over R. We may apply Pythagorean theorem because tangential is always perpendicular to the radial or the centripetal acceleration. From Pythagorean theorem, the total acceleration is equal to square root of A tangential squared plus A centripetal squared.